Hello, my name is Jenny Calahan. I am a graduate student at the University of Michigan, and I'm looking forward to telling you a little bit more about the project that I've been working on for the past few months, which is determining the 2D thermal profile of HD 163296. So why do we care about the temperature throughout a protoplanetary disk? Well, the temperature of the disk will affect the ways that we interpret observations. It will dictate the physical evolution of the disk as it is closely entwined with the local sound speed and viscosity, as well as the vertical flaring of the disk. And chemically, it will set the boundaries for snow lines. And snow lines have also been associated with key locations or chemical reservoirs for planet formation. An accurate thermal profile will have wide effects on interpreting many aspects of the disk, especially planet-forming mechanisms. And the disk around HD 163296 has planet detections within it, and it's a prime target for planetary formation theories. So the temperature structure around this disk in particular we deem to be really important. So how do we go about measuring the temperature throughout a disk? In this study, I use a combination of 6 high-resolution observations of CO and its isotopologues and a thermochemical model. Starting with observations, we use CO because it's very abundant within disks, and the different isotopologues we assume emit from different regions within the disk. So 12CO is the most abundant form of CO, so it's going to become optically thick higher up in the disk. So if we're looking down, it's going to be optically thick near the surface. And then 13CO is the next most abundant, so it's going to become optically thick a little bit lower than 12CO, and so on and so forth with 13C18O, C18O and C17O. And the observations that we're using are part of the MAPS program, and so we have really high resolution observations of around 26 AU is our beam size for the 1 to 0 transitions, and for the 2 to 1 transitions, it's about 13 AU. So then moving on to the Thermo-Chemical Code, we're using RAC2D. It takes in information about the physical structure of the disk, the radiation from the host star, chemical abundances, and for this project, we've initiated a CO depletion right at the start. So RAC2D then calculates the dust temperature in a nearly identical manner to RAD-NC3D, if you're familiar with that. And it goes on to calculate the gas temperature and chemical structure over time. At the end of a model run, we can then use ray tracing techniques to create simulated observations for the molecules available to us, and we can then compare our model directly to the ALMA observations. So we actually started with a base model of HD 163296 with a previously calculated CO depletion profile. And the way that CO depletion profile was calculated was after the gas temperature calculation of RAC2D. We found it important to deplete CO before the gas calculation because if CO is significantly depleted, then it would certainly affect the temperature structure, which is what we are primarily interested in. And using this CO depletion profile ended up producing radial profiles that didn't match observations at all. And so we needed to calculate a new CO depletion profile. And the way that we did that was an iterative process. We started with the originally calculated CO depletion, and we applied that to the model, and then we would figure out what we needed to change within the CO depletion to better reproduce the observations. And so we eventually found a different CO depletion profile that matched our observations much better. So then this is our initial model. We are comparing radial profiles from the observations and the model is in the dashed line, the observations are in the solid line. So you can see that we're doing a relatively good job matching most of the radial profiles except for 12CO. It's underpredicted by over 2 times at some radii, and we went through a whole parameter exploration to see if there was a combination of physical parameters that would heat up the layers in which 12CO emits from, while not affecting the other lines, and we ended up not finding any combination of available levers that would solve this problem. So we ended up hard-coding a solution. We artificially increased the temperature at which 12CO emits from. So this figure here shows the amount of heating that was added to the disk, and the blue line is the emitting surface of 12CO based on the observations using a method from PINT 2018. And I'll talk more about that later. Yeah, We ended up heating the surface above 0/R of 0.21, which corresponds roughly with the 12CO surface within 100 AU, and we increased the temperature following an inverse power law. We played around with some of these factors, the height at which we wanted to add the heating and the factor and the amount of excess heating we wanted to do, but we found this equation worked best. And we've identified two possible physical mechanisms that RAC2D doesn't take into account that could account for this excess heating. One is excess pause, perhaps via sintering. So within this region, the strongest heat source is from photoelectric heating. So if we just had more pause, that could account for the excess heat that we needed. Another option is mechanical heating. So this would be like physical movement in the disks from disk winds, stellar winds, or dissipation of gravitational energy from accretion through the disk onto the star. That is something that certainly affects the inner few AU of the disk that RAC2D just doesn't take into account. And so this could also account for the excess heating that we found necessary to match the observations. So with this excess heating, this is our final model comparing all of the different radial profiles. We're pretty happy with the way that each of these matched up. And so here is our final temperature structure. We have the gas temperature, we have the dust temperature, and I also show the difference between the gas and the dust temperature. This green area would be where the gas and the dust are coupled. And then right above that, there's actually a region where the dust is hotter than the gas. So we call that the overshoot region. And right above that, the gas is hotter than the dust. We can use these temperature profiles for interpreting future observations or answering further questions about temperature within this disk. We can then compare our model with the observed emitting surfaces. So we calculate the emitting surfaces using our simulated observations using the same technique as was used for the ALMA observations with ALMA, using methods again from PINT 2018. And we actually found right off the bat that our model reproduced the emitting heights pretty well. And we see that the emitting surfaces of optically thick molecules are yet another way to calibrate specific disk models to observations, especially in the outer few AU where radial profiles are not at all very sensitive. We can also compare our temperature structure to what has been derived directly from observations. So our observers were able to extract brightness temperatures over radius for the observed 2-to-1 transitions. And using the emitting surfaces to pull out directly measured temperatures, you can kind of create and directly probe temperatures throughout the disk. Our method of temperature extraction agrees really well with these directly measured temperatures. In the upper left, we overlay our temperature structure in the background and the observed temperatures in the points. You can see right away we do an okay job. And then each of these other panels, I'm plotting the temperature difference between my temperature and the directly observed temperature. And you can see that most of the points hover around 0 or at least are less than 10 Kelvin off, except for where we added the excess heat that we found necessary to match the radial profiles. We expect this is due to the directly measured temperature structures not having a high enough resolution or to be sensitive enough to temperature changes that are happening at really small scales within these regions. And next we wanted to explore gap temperatures. So our original model has a smooth gas surface density, but a large dust population that traces the observed continuum structure. We wanted to see what would happen to the temperature in the location of the gaps of the HD 163296 disk if we added gas gaps. We assumed that the depth of the gas gap would depend on the mass of the planet that lives there, so we focused on 2 gaps in particular, and we added gas gaps corresponding to a 1 Jupiter mass planet and a 4 Jupiter mass planet. So kind of an extreme value and then maybe a more expected value. You can see that adding a gas gap decreases the flux in the radial profiles, and we use the CO depletion profile to kind of rematch the model to the observations. And you can see that the CO depletion profiles at the location of the 2 gaps. Originally, there's a local minimum in the CO abundance, but adding a gap kind of forces us to increase the CO abundance in the gap. And lastly, we wanted to compare gap temperatures. So with those kind of rematched models that match the observations but have gas gaps, we wanted to see if the temperature structure changed at all. So over here, we have a zoom in of our gas temperature between 20 and 120 AU for our final model with a smooth gas surface density. And then over here, we show the difference between that model and a model with a gas gap. And so you can see at the location of the gaps, the temperature does increase. However, it only increases by upwards of 5%. So not a huge increase. And that's with the extreme value of a 4 Jupiter mass planet. So that was a really quick rundown of my project where I derived a 2D thermal structure of the disk around HD 163296. And I was able to compare this method of temperature determination directly with observationally derived properties of the disk, namely the emitting surfaces, brightness temperatures, and then I explored the temperature within the gaps of HD 163296, including effects of gas depletion within the gaps, and found that gaps could increase the temperature, but only upwards of about 5%. Thank you so much for listening to this whole talk. And if this was interesting to you at all, I do have a paper coming out, hopefully by the end of the year. Please check it out. All right. Thank you.